Hello again. In this video, we're going to look at logistic regression. Logistic regression is one of the approaches used when you want to use a dummy variable for your dependent variable. So first, what are dummy variables? Well, a dummy variable is a categorical variable where there are two states of nature. You're either something or you're not. So you're either a male or non-male. You're white or non-white. You're above or below an age, 60 years. Dummy variables are kind of useful because they allow us to compare different states that are exclusive of one another. For example, a treatment versus a control, and that's used a lot in scientific experiments. We might also be comparing different agencies, or maybe yes/no questions on a particular survey. As I've mentioned before, if you have categorical or nominal variables with multiple responses or multiple options, then you can turn those into dummy variables. They can be really useful when you're dealing with nominal variables. You can also combine dummies if there are multiple categories. But it's important to note that the number of dummies that you use must always be one fewer than the total number of categories. So for example, if your two categories are male and non-male, then you would use one dummy variable. 2 minus 1 is 1. If you're using months as dummy variables, then there are 12 months, 12 categories. So you'd use only 11 dummy variables, so single variables, where January is 1 for one variable, and then February is 1 for the next variable, and March is 1 for the next variable, and so on. And it's best in those cases to drop the average month. So why can't you use a dummy as the dependent variable in a standard OLS regression? Well, that comes down to the interpretation of coefficients in a standard regression. So when we're thinking about a 1 unit change in any variable equaling a coefficient value change in the y variable, then that approach does not work if the dummy is dependent, because the dummies are either 0 or 1. And so none of these examples shown here would add up to 1. So if our constant value b0 was 12.5, and our first coefficient, b1, was 20, if our x1 value was 3, that would give us a value of 3 times 20, 60, plus what 12.5 is 72.5. Y is 72.5. That is not 0 or 1. And so it would not work as a functional approach. So instead, we use logistic regression, or maybe some other form that's similar. Logistic regression is really just multivariate regression analysis with a specific type of dependent variable, which are usually dummy variables. You can also use other categorical variables in more expanded cases. Now, this approach could be used for any question where you want to look at the influence of different independent variables on the dummy dependent variable. So some examples that you might be interested in is whether in political voting, a respondent is likely to vote for Republican or not. Or maybe a Republican representative, maybe whether they're likely to vote for a particular congressional bill or not. You might also want to look at whether an organization has a particular position, or maybe a particular department or not. You might want to think about whether a person has been homeless or not. You might think about whether a person has been impacted by a new illness while in hospital or not. So as we've established, this approach requires a different interpretation of results, and they depend on whether you're using Logit or Probit models. So please see the handouts, and there's really good videos by Brandon Foltz that go into logistic regression in detail. So I'll cover it here in a bit of a surface level. So logistic regression is based on probabilities. In other words, we're calculating the probability that the dependent, i.e. dummy variable, is either 0, the not case, or 1, the yes case. But here there are odds and probabilities, which all gets very confusing. So we're thinking about the probability from 0 to 100%, from 0 to 1, of success. So let's say that the probability of success is 80% or 0.8. By definition, therefore, the probability of failure is 1 minus 0.8, which is 0.2 or 20%. The odds of a success are the ratio of the probability of success over the probability of failure. So the odds would be P success divided by P failure. The odds would be 80 over 20, or 0.8 over 0.2, which equals 4. Therefore, the odds of success are 4 to 1. That's where we get these gambling terms. You think of bookmakers and horses. If the probability of success and failure are 50-50, then it's 0.5 divided by 0.5, which is 1-to-1. For logistic regression, you may need to transform probabilities into odds and vice versa. For single variables, SPSS and the results output provide both odds and probabilities, which is great. The problem is when there are multiple variables, and here the calculation becomes a bit trickier. So as an example, the log odds, which is the kind of left-hand term that we're going to use, equals the constant term plus various coefficients related to their corresponding variables, as shown here. This is similar to the approach that you're going to use in your exercise. So you first need to establish what the variable values are. So for the dummies, it is usually yes equals 1 and no equals 0, regardless of that initial coding. But you do need to check what that coding is. So then you plug in all of the coefficient values from the SPS output and convert the answers into probabilities rather than odds. So the log odds is the equivalent of Z, which is the sum of all those terms above. So the constant plus the B1 age plus B2 times poll views plus B3 times reborn, etc. You can then convert these values into odds from the log odds by taking the exponent of both sides. So the exponent of log odds is just odds, and the exponent of Z is exponent of Z. Our probability is then the exponent of Z divided by 1 plus the exponent of Z. That's basically flipping around what we've done on the previous slide. So I know that's a bit complicated, but the payoff is here. So here's an example. The independent variable is the mother's age in years, and the dependent variable is whether the infant was breastfeeding at discharge from the hospital. This was a study in preterm infants, a group where breastfeeding is difficult because the mother gets home before the baby does. And so you can see here, the B is the coefficient for the constant, also called the intercept in the norm model. And then the XB is the exponential, and then the XB, EXPB, is the exponentiation of the B coefficient, which is actually an odds ratio. This value is given by default because odds ratios can be easier to interpret than the coefficient, which is in log odds units. So the significance value, the sig, is the score test that is used to predict whether or not an independent variable would be significant in the model. It's really similar to the p-values that we use in OLS regression. So in this table, the two numbers that you need to focus on are the slope, 0.157, and the intercept, which is 3.654 negative. A logistic regression model makes predictions on a log odds scale, and you convert this to a probability scale with those steps previously outlined. Suppose you want to get a predicted probability for breastfeeding for a 20-year-old mum. The log odds would be the constant term plus 20 years old times our mum age coefficient. So here the log odds is negative 0.514. If we take the exponent of both sides, we get just the odds term, and that odds term is 0.598. We then convert that from odds into probability, and this gives us a probability of 37%, which is a fairly low probability. In other words, there is a fairly low probability that a mother of a preterm child is going to breastfeed, according to this data. So you're going to be doing something similar for your exercise 7, and I do hope that the steps are not too complicated. I know they seem a little bit tricky. If you have any questions about them, please let me know.